Hello my dear students, welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous modules, we have seen what are the different modes of electromagnetic wave propagation. And the modes which we have discussed are transverse electrical, transverse magnetic and transverse electromagnetic waves. And then we have discussed what are the different types of waves, and these type of waves are classified based on the shape of the phase front. And we have seen that if we have point source, then you get spherical waves, and we have line source, we get cylindrical waves. And when we have parabolic antennas, we have plane waves where the phase is just dependent on the distance along the direction of EM wave. It is not dependent on any other factors. And then we have seen the planar approximation of spherical waves, because spherical waves are most common of all and plane waves are most easy to analyze. Therefore, planar approximation of spherical waves has seen that if you have spherical waves after considerably larger distances, these spherical waves can be approximated as plane waves. And then we have discussed a special class of waves called as uniform plane transverse electromagnetic waves, where not just the phase but the magnitudes of E and H are also dependent only on the distance of EM wave. Next, we have discussed a wave propagation parameter called intrinsic impedance, which is defined as the ratio of magnitudes of electric field and magnetic field at a given instant at any point. Thereby, we have also said that this can also be equals to E naught by H naught, where E naught and H naught are the initial values of electric field and magnetic field intensities. And for uniform plane wave, we have derived that the intrinsic impedance was equals to j omega mu by sigma plus j omega epsilon. And then we have discussed Poynting theorem, which says that the power leaving any closed surface is equals to the rate of decrease in energy stored inside electric and magnetic fields. In addition to this, if you have any ohmic losses, some of this energy would be lost in ohmic losses. In today's module, we would discuss what are the reflections and transmission of uniform plane transverse electromagnetic wave when it is being incident normally at a boundary. The contents we would be discussing in today's wave are the geometry of the problem, that is, here I would discuss the setup of the problem, and then I would discuss what are the fields along incident, transmitted and reflected waves, and I would analyze what are the fields inside two different mediums. As I said, there are two mediums, medium 1 and medium 2. So what are the fields inside these two medium will be discussed in the third section. And then I would discuss the boundary conditions to establish the relation among the fields inside medium 1 and fields inside medium 2. And then I would define a parameter called reflection coefficient, which tells us the amount of incident wave which got reflected to medium 1. And then transmission coefficient, which tells us the amount of incident wave which got transmitted to medium 2. So our conclusion is the discussion on this reflection coefficient and transmission coefficient. So once we discuss all these, I would analyze a dielectric conductor interface. That is, I have a special discussion where medium 1 is dielectric and medium 2 is conductor. This is just an example scenario. You can also analyze a dielectric interface. But for obvious reasons, medium 1 cannot be conductor because electric field won't exist inside a conductor. Therefore, there is no concept of EM wave propagation inside a conductor. The problem statement is that there is an electromagnetic wave which is traveling from medium 1 and it is reaching to medium 2. Please remember that the electromagnetic wave which we are discussing is uniform plane transverse electromagnetic wave. That is the same way we are discussing. So, uniform plane transverse electromagnetic wave is traveling from medium 1 and has reached to medium 2. Let us assume that the interface is at z equals to 0. That means when z is less than 0, we are in medium 1, and when z is greater than 0, we are in medium 2. The interface at z equals to 0, that means the boundary is an xy plane. And the boundary is xy plane at z equals to 0. Let the uniform plane wave be traveling along az cap in medium 1. Now at the interface, because the normal to xy plane is also az cap, the wave is incident normally to the boundary. Some part of the incident wave is transmitted to medium 2, whereas some part is reflected to medium 1. So what part is reflected to medium 1 and what part is transmitted to medium 2 is our analysis. So let us see the geometry associated. So this is medium 1 and this is medium 2 and this is the reason where z is equals to 0. So the normal to this is az cap, which is along this direction. To keep the consistency, where we have used the ax cap always to be going rightward, so this is ax cap. Now the relationship between unit vectors of Cartesian coordinate system are ax cap cross ay cap is equals to az cap. Similarly, az cap cross ax cap equals to ay cap is also a valid relation. Now, if this is az cap and this is ax cap, then ay cap would be using, I can obtain this using the right hand screw rule. I say that ay cap is this. There are three different waves in question. One is incident wave, which is traveling along az cap. The other is transmitted wave, which is also traveling along az cap. And then there is reflected wave, which is traveling along minus az cap. It is pretty obvious because if this is az cap, that is the direction of incident wave, the transmitted wave would also be in this direction, but the reflected back would be in the direction opposite to this. Therefore, the reflected wave is along minus az cap. Now let us also analyze the directions of electric fields and magnetic fields associated with the incident waves and transmitted waves. Now this is the direction of Poynting vector. The direction of Poynting vector means the direction of electromagnetic wave propagation. And for all these three waves, we say that the polarization did not change. When I say polarization is the direction of electric field intensity inside an electromagnetic wave. In detail, we would discuss about this polarization in the next module. But right now, we assume that the polarization did not change. That is, the direction of electric field intensity did not change, and that electric field intensity is assumed to be in the direction of ax cap. Now, if this is the Poynting vector's direction and this is the direction of electric field intensity, we know that the Poynting vector's direction is cross product of the direction of electric field intensity and the direction of magnetic field intensity. We also know that ax cap cross ay cap is equals to az cap. And this Poynting vector is along az cap and a bar is along ax cap. So for ah cap should be along ay cap. Therefore, the magnetic field intensity is along ay cap. Next, we have also seen this while we discussed in the previous module of EM waves. And for transmitted wave, this is the direction of Poynting vector, and this is the direction of electric field intensity. And pretty obviously, the direction of magnetic field intensity would be this. And the reflected wave, the Poynting vector is along minus az cap, and the direction of electric field intensity is along ax cap, because as I have said, the direction of electric field intensity is assumed to have not changed in all three waves. Now, if P bar is along minus az cap, electric field intensity is along ax cap, then the magnetic field intensity should be along minus ay cap. So the reflected wave's magnetic field intensity is along minus ay cap. Now that we have obtained the directions of electric fields and magnetic fields of all three waves, let us also analyze their phasors. For incident wave, transmitted wave and reflected wave, the transmitted wave and incident wave are traveling along az cap, and the reflected wave is traveling along minus az cap. The electric field is along ax cap and for all three. The expression for this phasor can be written as ei naught exponential of minus gamma 1z ax cap. Ei naught is the value of incident electric field at z equals to 0, and gamma 1 is the propagation constant. The transmitted wave is also along ax cap, and it can be written as et naught exponential of minus gamma 2z ax cap. Here it is gamma 2 because the gamma 2 is propagation constant for medium 2. And the phasor of electric field intensity for reflected wave is ERP bar is equals to ER naught exponential of gamma 1z, where ER naught is the value of reflected wave's electric field at z equals to 0, and gamma 1 is the propagation constant for medium 1, but the negative sign is absent here because the wave is traveling along minus az cap. The magnetic field along incident wave is along ay cap, and the magnetic field of transmitted wave is along ay cap, but the magnetic field of reflected wave is along minus ay cap. Therefore, HIP bar would be equals to Hi naught exponential of minus gamma 1z ay cap, and HTP bar is equals to HT naught exponential of minus gamma 2z ay cap, and HRP bar is equals to minus HR naught exponential of gamma 1z ay cap. Here, the negative sign is to indicate that the magnetic field is along minus ay cap, and the absence of negative sign here is that the wave is traveling along az cap, and gamma 1 is that the propagation is along minus az cap in medium 1. Now, the relationship between ei naught and hi naught can be written as eta 1 is equals to ei naught by hi naught, because the intrinsic impedance at any point inside a medium is the ratio of electric field intensity to magnetic field intensity. Similarly, eta 2 is also equals to et naught by ht naught. I can also say eta 1 here is equals to er naught by hr naught. Now that we have analyzed the values of electric fields and magnetic fields along three different waves, let us also analyze the values of electric field and magnetic field inside medium 1 and medium 2. So when we are in medium 1, the electric field intensity is because of the incident wave and also because of the reflected wave. So the total electric field intensity is sum of incident wave plus reflected wave. Therefore, the phasor of electric field intensity inside medium 1 is equals to the phasor of incident wave plus the phasor of reflected wave. From the results which we have obtained earlier, E1 P bar is equals to EIP bar plus ERP bar. Similarly, the magnetic field intensity is also because of two components, that is the incident wave and the reflected wave. Therefore, the magnetic field intensity inside medium 1 is equals to Hi bar plus Hr bar, and the phasor of magnetic field intensity inside medium 1 is equals to Hip bar plus Hrp bar. So, if I substitute the results which I got earlier, I get Hi naught exponential of minus gamma 1 z Ay cap minus Hr naught exponential of gamma 1 z along Ay cap. Understand that there is positive sign here and there is negative sign here because the electric field intensities are in the same direction, but the magnetic field intensities are in the opposite direction. So for medium 2, the electric field intensity is just because of the transmitted wave. Therefore, E2p bar is equals to ETp bar, which was equals to ET naught exponential of minus gamma 2z along Ax cap. The magnetic field intensity is also because of the transmitted wave. Therefore, H2 bar is equals to Ht bar and H2p bar is equals to Htp bar. And we have obtained that to be equals to Ht naught exponential of minus gamma 2z along the direction of Ay cap. Now to discuss the boundary conditions, please remember that I have a boundary here for z equals to 0. And in medium 1, I have electric field intensity to be equals to Ei naught exponential of minus gamma 1z plus Er naught exponential of gamma 1z. These two are in the direction of Ax cap. Similarly, I had magnetic field intensity along the direction of Ay cap, whose magnitude was equals to Hi naught exponential of minus gamma 1z minus Hr naught exponential of gamma 1z. This is in the direction of Ay cap. Similarly, inside medium 2, I have electric field intensity along the direction of Ax bar, which is equals to Et naught exponential of minus gamma 2z. And the magnetic field intensity along Ay cap, whose magnitude is equals to Ht naught exponential of minus gamma 2z. This is along Ay cap and this is along Ax cap. Now, whatever happens when z is negative is the medium 1's headache, and what is happening in medium 2 is the concern of medium 2. That is, when z is greater than 0, it is concern of medium 2, and when z is less than 0, it is of medium 1. But at z equals to 0, it is the interface. Now, there would be the values of electric fields and magnetic fields even at the interface. But the values of electric field at interface can only be one value. It cannot have two different values. Similarly, the value of magnetic field intensity at z equals to 0 should also be unique. It cannot have multiple values. So keeping that in mind, let us look at the boundary conditions. The component along the normal to the boundary is 0. There is no normal component because normal component is along Az cap, and we don't have any vector along Az cap because of transverse electromagnetic nature of the wave. And at z equals to 0, because these two values should be equal, whatever is the value of electric field intensity at medium 1 at point 0 should be equals to the electric field intensities inside medium 1 at z equals to 0. Therefore, if I substitute z equals to 0 here in both sides, I get Ei naught plus Er naught to be equals to Et naught. Let me erase this and let us also analyze the magnetic field intensity. So the magnetic field intensity, again the component along the normal is 0. Therefore, at z equals to 0, I can say that H1p naught is equals to H2p naught. From this, if I substitute z equals to 0 here, I get that Hi naught minus Hr naught to be equals to Ht naught. We have already discussed that Ei naught by Hi naught is equals to eta 1, which is also equals to Er naught by Hr naught. Similarly, Et naught by Ht naught is equals to eta 2. Therefore, if I use that relation, This Hi naught minus Hr naught I can written as Ei naught minus Er naught by eta 1, and Ht naught can be written as Et naught by eta 2. If I try and determine the values of Et naught from this, I get that Et naught is equals to eta 2 by eta 1 times Ei naught minus Er naught. This is eta 2 by eta 1. Similarly, if I get the value of Et naught from this, it is equals to Ei naught plus Er naught. From these two equations, I get to conclusion that Ei naught plus Er naught should be equals to eta 2 by eta 1 times Ei naught minus Er naught. If I bring the electric field intensities to one side and intrinsic impedances to the other, I get that Ei naught plus Er naught by Ei naught minus Er naught to be equals to eta 2 by eta 1. If I use the componendo dividendo, or in other words, I may use dividendo componendo here for my comfort. If I use dividendo componendo, it has three parts. The first part is I subtract 1 from both sides of the given equation. The second part is I add ones to both sides of given equation. The third part is I divide the equations obtained from operation 1 and operation 2. And then I would get the result of dividendo componendo. Right? If I do that, if I subtract 1 from both sides, if I do minus 1 and minus 1, the LCM would be Ei naught minus Er naught. So I would be getting Ei naught plus Er naught minus Ei naught minus Er naught divided by Ei naught minus Er naught, which is equals to, from this I get eta 2 minus eta 1 by eta 1. Right? If I add 1 to both sides of this equation, I get Ei naught plus Er naught plus Ei naught minus Er naught divided by Ei naught minus Er naught to be equals to eta 2 plus eta 1 by eta 1. Now if I subtract these, I get Ei naught here and Ei naught here will cancel. I get 2 Er naught by Ei naught minus Er naught. Here from this I get these two get cancelled. 2 Ei naught by Ei naught minus Er naught. If I divide these two equations, because the denominators here and here are same, they cancel out, and the denominators here and here are cancel out. I get Er naught by Ei naught is equals to eta 2 minus eta 1 by eta 2 plus eta 1. Now the reflection coefficient is the portion of incident energy which reflects back. It is defined as Er naught by Ei naught. If you determine Hr naught by Hi naught, you would get the same result, spelled as gamma. So gamma equals to eta 2 minus eta 1 by eta 2 plus eta 1. The transmission coefficient is defined as the portion of incident energy which passes through and reaches the second medium. It is defined as Et naught by Ei naught. And Ei naught plus Er naught is equals to Et naught. From the earlier result I have obtained, I can write Ei naught plus gamma Ei naught to be equals to Et naught. So if I take Ei naught common, I can say Ei naught times 1 plus gamma equals to Et naught, where I have obtained gamma to be equals to eta 2 minus eta 1 by eta 2 plus eta 1. Therefore, if I do 1 plus this, I would be getting 2 eta 2 by eta 2 plus eta 1. This is the amount of energy which gets transmitted to medium 2. So these are the reflection coefficients and transmission coefficients in general. Let us see what would happen if medium 1 is perfect dielectric and medium 2 is perfect conductor. We know that eta is equals to root over of j omega mu by sigma plus j omega epsilon. If it is a perfect dielectric, then it does not conduct. Sigma is equals to 0. Therefore, eta is equals to root over j omega mu by 0 plus j omega epsilon. J omega cancel. That is equals to mu by epsilon. So, for perfect dielectric, when sigma equals to 0, the intrinsic impedance is equals to root over mu by epsilon. And for perfect conductor, when sigma is equals to infinite, then the intrinsic impedance is 0 because eta equals to j omega mu by sigma plus j omega epsilon is equals to root over j omega mu by infinite plus j omega epsilon. Now, because this is infinite, this can be eliminated. So the answer is sigma 1 by infinite to be equals to 0. So the intrinsic impedance of perfect conductor is 0 and the intrinsic impedance of perfect dielectric is root over mu by epsilon. We have that the transmission coefficient is equals to 2 eta 2 by eta 2 plus eta 1, but here I have eta 2 is equals to 0 and eta 1 is equals to root mu by epsilon. Therefore, the transmission coefficient is 0 and the reflection coefficient is minus 1. The meaning of this results is there is no wave propagating into the conductor. The entire wave is reflected back. Because medium 1 is perfect dielectric, sigma equals to 0, which also means that alpha is equals to 0. That is, attenuation constant is 0, because you may remember attenuation constant to be equals to omega times root mu epsilon by 2 times sigma by mu epsilon whole square plus 1 minus 1, which here this is under root. So if this is equals to 0, the answer from this is 1. 1 minus 1 is 0. Attenuation constant is 0. So the attenuation constant for perfect dielectric is 0. And gamma is equals to, you know that gamma equals to alpha plus j beta. If alpha equals to 0, then gamma is equals to j beta. So from the value of electric field intensity's phasor in medium 1, which is equals to E I naught exponential of minus gamma 1z ax cap plus E R naught exponential of gamma 1z ax cap, I can write that this to be equals to E I naught exponential of minus gamma 1z ax cap minus E I naught exponential of gamma 1z ax cap. The minus here is because E R naught by E I naught, where I have obtained, is equals to minus 1. The gamma, just now I have seen that to be minus 1. Therefore, E R naught can be replaced by minus E I naught. And gamma is equals to j beta 1. And exponential of j beta 1z minus exponential of minus j beta 1z is equals to 2j sin beta 1z. So the value of phasor inside medium 1 is E1 P bar is equals to minus EI naught times 2j sin beta 1z in the direction of ax cap. This is the phasor of electric field intensity inside medium 1. Let us determine the phasor of magnetic field intensity inside medium 1. I know that magnetic field intensity inside medium 1 is equals to h I naught exponential of minus gamma 1z ax cap minus h r naught exponential of gamma 1z ay cap. Here I can write this to be equals to h I naught exponential of minus gamma 1z ay cap plus h I naught exponential of gamma 1z ay cap, because E r naught by E I naught is gamma. I can also write this to be equals to h r naught times eta 1 by h I naught times eta 1 is equals to gamma. If I cancel them, I write H R naught by H I naught is also equals to gamma, and the gamma value we have obtained to be equals to -1. Therefore, H1 P bar is equals to H I naught exponential of minus gamma 1 Z A y cap plus H I naught exponential of gamma 1 Z A y cap. Again, if I add them, I get 2 cos beta 1 Z A y cap. This is the phasor of magnetic field intensity inside medium 1. Now that we have phasors, let us try to determine the time variant versions. Because you know, time variant versions can be obtained by taking the real part of phasor multiplied by exponential of j omega t. Let us try to determine the time variant versions. The phasor of electric field intensity inside medium 1 is minus ei naught 2j sine beta 1z along the direction of ax cap. And the phasor of magnetic field intensity is equals to h I naught 2 cos beta 1z ay cap. So the magnetic field intensity can be obtained as real part of h1p bar exponential of j omega t, and the electric field intensity can be obtained as the real part of e1p bar times exponential of j omega t, where e1p bar is the above result, and j omega t can be split as cos omega t plus j sin omega t. In that, if I obtain the real part, the cos omega j sin omega is complex part, but j times j is real, and j square is -1, minus times of minus is plus. I get this to be equals to 2 I naught sin beta 1z sin omega t. If you want me to explain, I do that. See, here it is j, let me say you have ja times x plus jy, then it can be split as minus ay plus j times ax. Here I already have minus sign. If I include this minus sign here also, I get plus jy minus jx. The real part is ay. So here this is a and this is y. Therefore, the real part is 2 I naught sin beta 1z sin omega t in the direction of ax cap. And from this, I get, if I do the multiplication, this is real and this is imaginary. Therefore, I get 2h I naught cos beta 1z cos omega t along the direction of ay cap. You may see the amplitudes are constant. Only the phase is changing with space and time. These waves are called as standing waves. The standing waves are where the energy is retained. The energy never ceases. So you would get standing waves when an electromagnetic wave from a perfect dielectric is impacting with an perfect conductor. An assignment to you is determine the expression for standing wave ratio. These are the references for today's lecture. Thank you for your attention. For any questions, please ask in the comment section. Meet you in the next module. Thank you.